jump into today's material. So here's an overview of what we'll be discussing. So this was a question we started answering last Friday. The question is, how does the body extract energy from food? And we were looking at how energy can be extracted from three macronutrients: from carbohydrates, from proteins, and from fats. So we'll talk about some specific pathways. So the aerobic and anaerobic pathways will be used by carbohydrates to make ATP. In beta oxidation is something which is a step unique to the breakdown of fats, and deamination is a step unique for the breakdown of proteins. But after beta oxidation and deamination, we'll see how those products will, from deamination and beta oxidation, will eventually enter the aerobic pathways. After that, we'll talk about the connection between metabolism and respiration at a cellular level. We'll see why is it necessary for us to breathe in oxygen and how is carbon dioxide being produced, and we'll see how various macronutrients can be broken down in that process. And finally, we look at what are the various types of fuels used by the body for various activities. For example, when you look at high intensity activity versus endurance activity, depending on the duration of the activity, the type of fuel used by the body to make ATP can vary. And finally, we look at muscle performance and fatigue as well. So this is a slide we saw on Friday. We were looking at the various pathways through which carbohydrates can be used to make ATP. All right, and we see that the first step is glycolysis, and we see that glycolysis will require around 10 different steps. But as far as we are concerned, we just look at what is the substrate going into glycolysis and what is the product being produced, right? And so we see that as a result of glycolysis, pyruvate is produced. Glucose has got 6 carbon atoms, and two pyruvate molecules each have 3 carbon atoms, right? And then we'll see how pyruvate can be converted into acetyl-CoA inside the mitochondria, and then acetyl-CoA is going to enter the citric acid cycle, which will release a lot of high energy electrons, and all of those high energy electrons will be taken to the electron transport chain, where lots and lots of ATP can be synthesized. So we see that pyruvate has two options. It can either be converted into lactate, or it can be converted into acetyl-CoA. And on Friday's lecture, we saw what was the reason for pyruvate to be converted into lactate, and the reason is when there is a lack of oxygen, or when the ATP needs to be produced very quickly. That's when pyruvate can be converted into lactate. So if you want to know a little more about that, we already discussed it on Friday's lecture. Now we're seeing what happens to pyruvate when it is not made into lactate. So we see that pyruvate is going to be converted into acetyl-CoA, and notice that there are 3 carbons in pyruvate. The first carbon is going to be lost as carbon dioxide, and this is the first time I'm explaining why our body is producing carbon dioxide during the production of ATP. So we see 1 carbon is lost as carbon dioxide, and the remaining 2 carbons, they're going to be linked to this molecule known as coenzyme A to form acetyl-CoA. Now in this step, we also notice that there are actually 2 pyruvate molecules, and so if it's going to take the aerobic metabolism pathway, there will be 2 acetyl-CoA molecules being produced. Keep in mind that there were 6 carbons in the glucose molecule, and then you have 2 pyruvates, each has 3 carbon atoms, and then each of those pyruvates will be made into acetyl-CoA, so you'll have 2 carbon dioxides released and 2 acetyl-CoA being produced. And this is an irreversible step. Once pyruvate has been converted into acetyl-CoA, there's no going back. Acetyl-CoA is going to move on to the next step in the aerobic metabolism. And the next step in the aerobic metabolism is acetyl-CoA entering into the citric acid cycle. So let's look at the name citric acid cycle and see why it has such a name. So let me draw your attention to the word cycle, right? And you'll notice that in the very last step of the citric acid cycle, you have oxaloacetate being produced, And in the very first step of the citric acid cycle, oxaloacetate is going to be involved as a substrate. Let me repeat, in the very last step of the citric acid cycle, oxaloacetate is produced as a product, and in the very first step, oxaloacetate is the substrate involved in this pathway. And notice that oxaloacetate has got 4 carbons, and acetyl-CoA has got 2 carbons from the glucose molecule. And so these 6 carbons will be combined to form citric acid, right? And that is why this is called a citric acid cycle, because in the very first step you have citric acid being produced, and in the very last step you have oxaloacetate being regenerated. So it's a cyclic pathway. Is this clear why it's called citric acid cycle? Yes? Okay. Now we find that each of these carbons from the acetyl-CoA, which combine with oxaloacetate to form citric acid, each of those carbons will be lost as carbon dioxide. So you see, every single carbon atom which was found in that glucose molecule in the first step of glycolysis has all been converted into carbon dioxide, right? So I hope this explains why we need oxygen and also why carbon dioxide is being produced. As we go further down in these pathways, we'll see another important role for oxygen as well. And in addition to carbon dioxide being produced, there are a number of high energy electrons which are released, and the actual ATP produced through citric acid cycle is very little. Notice that there is one GTP molecule being produced, that is guanosine triphosphate, and GTP can easily be converted into ATP, right? So for the sake of our discussion, we can consider this as one ATP molecule produced per citric acid cycle. And since you have 2 acetyl-CoA, the entire citric acid cycle will happen twice, and so you'll have 2 GTP molecules being produced. All of the high energy electrons which are released, they will be carried by electron transporters, namely NADH and FADH as well, and there will be 3 NADH molecules generated from a single citric acid cycle and 1 FADH2 as well. And in the last step, notice that oxaloacetate has been regenerated. Okay, and so this keeps on happening over and over again. And just to remind you, because there were 2 acetyl-CoA molecules produced from that first glucose, there will be citric acid cycle occurring twice. Okay. Any questions until this point? This is a very high-level view of what's happening in these pathways. If you take a biochemistry course, you will get into all the details. Right? Yes.
Is we anaerobic pathway because of the amount of oxygen, or where's all the oxygen coming from?
I'll explain where oxygen will be used further on. But yes, this is all aerobic metabolism, because carbon dioxide is produced and oxygen is being used as well. In order to make the carbon dioxide, you need oxygen, but there is another use for oxygen which I will explain in the electron transport chain. So in the electron transport chain, as I mentioned, NADH and FADH2, they are going to deliver their high energy electrons, and these electrons, they are going to give up their energy, and that energy is used to link ADP or adenosine diphosphate to inorganic phosphate, and when those two are combined, it forms the ATP, adenosine triphosphate. And where this electron transfer chain occurs is going to be inside the mitochondria. Now the mitochondria, it's a doubled membraned structure, so it's got 2 lipid bilayers, right? And so it is in this inner mitochondrial membrane where the electron transport chain is going to take place. So let me just orient you to what we are seeing in this picture. So this yellow part here is the cytosol, and here you have the outer mitochondrial membrane, and deeper to that you have the intermembrane space, the space between these 2 membranes, and then you have the inner mitochondrial membrane. And in this inner mitochondrial membrane, the electron transport chain is just shown as this white color box, but in truth there are actually 4 different protein complexes, and these electrons will be transferred from one complex to the other. And as these electrons are being transferred from one complex to the other, they will give up their energy, and all of these energy depleted electrons, they are going to combine with oxygen and also with the hydrogen ions to eventually form water, right? So this is a very important step where out of the energy depleted electrons, they are going to combine with oxygen and hydrogen ions to form water, right? And if this step is affected, in the electron transport chain, an individual will die because the body is not able to make more and more ATP. So it's a very crucial step, and this is why we need oxygen so that ATP production can continue. And even in the previous steps, we saw that those carbons which were released from glucose, they eventually turn into carbon dioxide as well. And so it's not surprising that many poisons will affect this part in the electron transport chain, and that's how it can lead to the death of an individual. And yes, without oxygen, ATP production is going to stop, right? This final step in the electron transport chain will be stopped. So now let's see how all of the high energy electrons, they are going to be used for making ATP. Right? Let's see how all of this energy is used to make ATP. So here's a figure where you see that the electron transport chain is depicted as these four complexes. You have complex 1, complex 2, complex 3, and complex 4. And there are still a lot of things which we don't understand about the electron transport chain, right? So what we discuss here is at a high level. Even if you were to take a more advanced biochemistry course, they'll still tell you that much of this is a black box, right, as far as to what's going on in these complexes. And so we find that the NAD is going to give up its electrons at complex number 1, whereas FADH2 is going to give up its electrons at complex number 2. And as these electrons are being passed on from one complex to the other, we see that hydrogen ions from the mitochondrial matrix is going to be pumped into the intermembrane space. Let me repeat that. As electrons are moved from one complex to the other, hydrogen ions, or in other words protons, they're going to be pumped from this mitochondrial matrix into the inner membrane space. And so as a result, we see that there's a pretty high concentration of protons or hydrogen ions in the inner membrane, in the intermembrane space. And this leads to an electrochemical gradient. And the term electrochemical gradient is something we talked about in the nervous system. You see that there is a chemical gradient because you have higher concentration of protons in the intermembrane space. Secondly, these positively charged ions, they are going to be attracted towards the mitochondrial matrix because it is got a higher negative charge. And so all these hydrogen ions, the way they can get back into this mitochondrial matrix is through the ATP synthase enzyme, shown here as this purple complex. Right? The way these hydrogen ions can get back down this electrochemical gradient is through the ATP synthase enzyme. And as these hydrogen ions flow through this ATP synthase enzyme, this entire complex here is going to keep rotating over and over again, and it's got these 3 pockets, and to those pockets you have ATP and inorganic phosphate binding, and as this complex rotates, it allows the inorganic phosphate to be linked to ADP, and that's how ATP is going to be formed. So repeat, as the hydrogen ions are flowing down this gradient, the complex rotates, and that allows the ATP to be synthesized by ADP being linked to the inorganic phosphate, right? And that is how you have around 25 molecules of ATP being generated from a single glucose molecule, whereas if with just glycolysis and the Cori cycle, you would have only a lot less ATP being produced. So are there any questions for me before we proceed? Okay, if not, here's a think, pair, share activity. When you're jogging at a relaxing pace, why is it that you can go on for around an hour, right? However, if you are sprinting, you cannot sustain it for more than a couple of minutes, right? So this is an opportunity for you to turn to your neighbors or to your TAs and discuss, and then we'll talk about the answer. And I want to qualify what we mean by relaxing pace, right? I've met people who run 5-minute miles and it's a relaxing pace for them. once in my lifetime. Probably a decade ago, I did a 7-minute mile and I thought I was going to die. All right. So the term relaxing pace can really vary from person to person. Maybe 10 to 12-minute miles, that's relaxing pace. So, but why is it that if it's a high intensity activity, you cannot sustain it for more than a couple of minutes or maybe a minute at the most, right? So yeah, discuss and then we'll see what the answer is.
My PI in the laptop.
All right. So does anyone have any thoughts? I'm not going to call out any specific TA, but do you guys have any thoughts? Anyone wants to share? Yes. Yeah, that's correct. So just to repeat what was said, when you're going at a relaxing pace, your body is going to use more of the aerobic pathway, whereas in the anaerobic pathway is probably what you're using when you have a high intensity activity. So the amount of ATP generated will be a lot more using the aerobic pathways, and so you'll get more amount of ATP produced for the same amount of substrate. All right. So let me just explain what I just now said using a recap of the carbohydrates metabolism. And what I show you in this slide is what I think you need to know, right? So the two things I mentioned is know what is the substrate entering into a pathway, what is the product produced, and also keep in mind where the carbon atoms are going, right? So, and maybe a third thing too, just know which one produces more ATP. So we see that glucose molecule has got 6 carbon atoms, right? And we see that when it undergoes glycolysis, which has around 10 steps, but here all you see is one nice arrow, right? It produces 2 pyruvates. Each pyruvate has got 3 carbons in it. And in this 10 steps of glycolysis, you only make 4 ATP, right? Which is not much. And we see that there is a few high energy electrons which are released, and those are carried by the NADH carrier. Now pyruvate can be converted into lactic acid, which also has got 3 carbons in it when you don't have as much, we don't have oxygen available, and that lactic acid will be taken to the liver where it will undergo gluconeogenesis. Lactic acid will be turned back into pyruvate, which will again be turned back into glucose. Now this is happening in the cytoplasm, and this is an anaerobic pathway because there's no oxygen being used. And the benefit of this anaerobic pathway is that ATP is produced very quickly because there are fewer steps, and that's the goal. The body wants to make the ATP very quickly. However, let's say there is not a need for that ATP to be made as quickly, then the aerobic pathway is going to be activated. And notice that pyruvate will be transported into the mitochondria where it can be converted into acetyl-CoA. Notice that among the 3 carbons in pyruvate, one of them is going to be lost as carbon dioxide. The remaining 2 carbons will be linked to this coenzyme A molecule to form acetyl-CoA. And there will be 2 acetyl-CoAs because you have 2 pyruvates which were produced from glycolysis. Now acetyl-CoA is going to enter the citric acid cycle, and in this citric acid cycle we see that the amount of ATP produced is very limited. For each citric acid cycle you will have 1 ATP, so because you have it happening twice with 2 acetyl-CoA molecules, you'll have 2 ATP produced. You will have also each of those carbons from the acetyl-CoA molecule, they'll be lost as carbon dioxide, and there is high energy electrons released, and those are going to be carried by the electron carriers NADH and FADH2. And these high energy electrons, they are going to be passed on through the various complexes in the electron transport chain, and we find that those energy depleted electrons will combine with oxygen and hydrogen ions to form water. But notice that the amount of ATP being produced as a result of this aerobic pathway is going to be around 25 compared to 4 ATP molecules in the anaerobic pathway. And so that is why when a person is sprinting and needs the ATP to come to be produced very quickly, the body would use the anaerobic metabolism, whereas if you are engaging in a more endurance activity like say a half marathon or maybe a 5-mile run, the body would use the aerobic metabolism, and you can sustain such an activity for a longer period of time because you have more bang for your buck. You have more ATP produced from the existing substrate. Is that clear, folks? Yes. Why we cannot sustain an activity for a long time if the intensity is very high. Is this level of detail overwhelming, or is it okay to deal with for metabolism? All right, great. So now let's talk about how the body is going to extract energy from fat. And if you understand this, fat metabolism is very simple to comprehend. So we see that it's going to start with the breakdown of lipids, or lipids are also known as triglycerides, and we see that a lipid molecule has this glycerol backbone. The glycerol backbone has got 3 carbons. To each of those carbons you have a chain of fatty acids linked, and we see that each fatty acid chain has got lots and lots of carbons in it. And a lipase enzyme will break this glycerol backbone from the fatty acids. So how many carbons are there in this glycerol backbone? I just now mentioned how many? 3. Yes, so 3 carbons are there in this glycerol backbone, and so with very few modifications it can fit right into the glycolysis pathway, right? And so you will have 1 pyruvate being produced from a single glycerol molecule, and that will give rise to a certain amount of ATP. Now the remaining fatty acids, they will be converted into acetyl-CoA through a process known as beta oxidation. Okay, so beta oxidation is where you have the carbon number 2 from the carboxylic end. That's where there will be a break made. So we have the beta carbon here, and these 2 carbons, they will be linked to coenzyme A, and when those 2 carbons along with coenzyme A are removed, acetyl-CoA is going to be formed, and that will enter the citric acid cycle. So for every 2 carbons will be used to make acetyl-CoA, and that will enter right into the citric acid cycle. So we see that from a single fat molecule you can have a lot more ATP being produced depending on the length of the chain of the fatty acids, right? And we see that from acetyl-CoA you'll have a lot more high energy electrons being generated, and those are carried by NADH and FADH2 as well. Is this clear, folks, how we get a lot more ATP from a single fat molecule? Okay. So now the question is, how does the fat get into the mitochondria, right? And there is this molecule known as carnitine, which is able to transport the fat into the mitochondria. And so because obesity is such a concern in this day and age, companies are always looking for ways to sell things to you to help increase fat burning, right? So there are some health claims that if you were to take more carnitine in your diet, that can help increase the amount of fat being burnt, right? And this seems logically a plausible explanation, but there is some controversies related to this. People say that it can also lead to muscle weakness. All right, so usually if there's money involved, there will be people will be overselling a product to you. So that's something to keep in mind. This is clear why carnitine is sold, because they think more fat will be burnt in the mitochondria. So now we move on to extracting energy from proteins, and the only time the body is going to use proteins to make ATP is during starvation, right? When you have times of starvation, the brain has to ensure that its function is continued, and so only in such times will proteins be broken down into amino acids, and those amino acids can be sent to the liver, and then it can be used to make glucose. But we see that in an amino acid there is this amino group, as we all know, and this amino group is something which our body cannot metabolize, and so there's a process known as deamination, which will strip off this amino group and it will excrete it in the urine, right? And that's how the remaining carbon skeleton is going to enter the catabolic pathway. And so having too much meat in the diet can result in an excess burden on your body in trying to deal with all of this excess urea which is going to be produced. So we find that the remaining carbon skeleton will enter the catabolic pathways depending on the structure of the R group. You know that there are 20 different R groups, and depending on the structure of the R group, these remaining carbon skeleton can enter different parts of the catabolic pathway. For example, if there is alanine, it's going to be converted into pyruvate and it can enter the metabolic pathway in that step. Whereas if you consider methionine, it's going to enter somewhere in the middle of the citric acid cycle. So here's the question, right? So which do you think will generate more ATP and why? Do you think alanine can generate more ATP, or do you think methionine will generate more ATP? You can just take a couple of minutes to fill out this poll everywhere. Okay, how many of you think it's methionine? How many of you think it's alanine? Okay. So most of you picked alanine, and that is correct, right? Because we find that because alanine is entering earlier on in this catabolic pathway, it will end up making more ATP because you have more high energy electrons being released along the entire pathway than further down in this pathway. So I haven't told you why this is the case, but there will be around 12.5 ATP molecules produced by alanine, and methionine will produce only 5 ATP molecules. And the reason is NADH will lead to more ATP being synthesized than just FADH, right? And if you want to know the reason why, we can discuss after class. It's something beyond the scope of our discussion. But it really depends on where in the catabolic pathway the carbon skeleton enters in to see how much ATP is going to be produced. Any questions? Yes? Okay, and we are only going to mainly consider ATP synthesis from fats and carbohydrates because proteins being used to make ATP is an exception, right? I don't think most of us in this room are making ATP from proteins. So now we answer the second question: how is metabolism related to respiration? And I need to introduce this term to you. It's known as RQ value, or the respiratory quotient, and this is an index of the nutrient which is being used by the body to make ATP. Right? This is an index of the type of nutrient being used by the body to make ATP. So the way they calculate RQ value is by taking the volume of carbon dioxide which was exhaled or produced divided by the volume of oxygen being used. So in a laboratory setting, they could take individuals and put a mask on their face and see how much oxygen they're consuming and how much carbon dioxide is being produced, and that can be a way to determine a person's RQ value. But we also see that from the laboratory setting, these following values were determined as well. So we could take pure carbohydrates and burn it and see how much oxygen was used and how much carbon dioxide was released, and repeat the same thing for proteins and fats as well. So when you think about a meal, it's going to have a mixture of all of these, so it really depends on the distribution of fats, proteins and carbohydrates. So these are just some equations I wanted to show you on how they came up with these values, right? So I've not put this slide in the handouts because I don't want you to think it's something you're responsible for, but just I hope you remember these three values. For carbohydrates, the RQ value is close to 1. For fats, it's around 0.7, and for proteins, it's around 0.8. So rather than using this equation, we can also think about the various steps in aerobic and anaerobic metabolism, and we can understand why carbohydrates have a higher RQ value. So when you think about the breakdown of carbohydrates, we see that carbohydrates can be metabolized by both the aerobic and the anaerobic pathway. And whenever carbohydrates are broken down through the anaerobic metabolic pathway, it's going to use less oxygen, right? And if it uses less oxygen, then the denominator is going to be smaller, and that's why the RQ value gets bigger, right? Whereas when you think about proteins and fats, they're mainly going to be broken down through the aerobic pathway, right? Meaning that the denominator is going to get larger. And let me just explain why. If you think about fats, most of the fat will be converted into acetyl-CoA, which is going to enter the citric acid cycle in the mitochondria. And also, depending on the carbon skeleton, most of amino acids will also be entering the citric acid cycle as well, and that is why you have a higher RQ value for carbohydrates compared to proteins and fats. Does that make sense? Yes. So I hope you are just not memorizing those three numbers, but you understand why RQ value for carbohydrates is higher than for proteins and fats. So now I want to talk to you about the various types of fuels as they're being used during various activities. How does that impact the RQ value? Okay, so here is a graph showing you RQ value on the y-axis, and then on the x-axis you have time shown in terms of seconds. Okay, and so when a person is at rest, as all of you are, as all of us are, we see that the RQ value is going to be around 0.8. Right, and you may see this value 0.8 and think, okay, when we are at rest, are we using proteins? Because I told you value of 0.8 is the RQ value for proteins, but that's not the case. Right? When we are at rest, the body uses both carbohydrates and fats to make ATP. And if you take the average of 0.7 and 1, what's the value you get? If you take an average of 0.7 and 1, 1 plus 0.7 divided by 2, was it 0.85? So it's around 0.8, right? So that is why when you are at rest, you have an RQ value of 0.8. Is that clear? Yes? Yes, yes, okay. When I asked you what's the average of 1 and 0.7, everyone was just silent. So can we move on? Yes? Okay. But then when there is an initial burst of activity, the body uses creatine phosphate to make ATP. Okay, so this initial burst of activity would last for around 0 to 10 seconds, and when creatine phosphate is being used to make ATP, notice that there is no change in the RQ value because the body is not using proteins, carbs or fats in addition to that current point in time, right? So there's no change in RQ value for that initial burst of activity. But then after some time, we see that as the activity continues beyond 10 seconds or so, and I'm giving approximate values here because it really depends from person to person to see how much creatine phosphate is stored. We see that the body will start using carbs, and so the RQ value starts increasing, and as the intensity keeps on going further and further, eventually fatigue can set in, or also the carbohydrates stores are being depleted, so the body will start using fats, and consequently you will notice that the RQ value is dropping back down closer to 0.7. Okay, so let me give you like a real life scenario to explain these numbers. All right, so here you're sitting in class listening to what I'm saying, and then I suddenly put up the polar bear question, right? And so you go to pick up your phone so that you can scan the code and you can answer it, and guess what, you can't find your phone, and you start panicking, and you're like, where did I drop it, and if let's say the class where you were, maybe you just remember I was sitting outside in the hallway and I was watching this video or I was texting someone, and so you quickly run outside and within 10 seconds you find your phone, right? Has your RQ value changed? Yes. How many of you think it has changed? How many of you think no, it's not changed? Okay, thank you. All of you said no, it's not changed. You are right. Your RQ value won't change because that initial burst of activity to go grab your phone from the hallway was within 10 seconds, and so the RQ value hasn't changed because your body has used creatine phosphate. But let's say you were in the student center, right, and you remember watching videos on your phone when you were there. So you're running there, and so the initial burst is over, and then your body starts using carbohydrates to make ATP, and so the RQ value is going to change. Let's say it's further from the student center and you are at the rec center, right? So you're running really hard, really hoping that the new phone you bought has not been picked off by somebody else. And so you're running really hard and you're getting close to a value of 1.0, and then slowly fatigue starts to set in, right? We have lactic acid building up in your muscles, and you're no longer able to push yourself with the same intensity. And as the intensity at which you're exercising your muscles is decreasing, the RQ value is going to start slowly dropping, right? And let's say you're depleting the carbohydrates in your muscles, right, the glycogen in your muscles, then you're starting to use more and more fats, and the RQ value drops further and further. But finally you find your phone, all right? So happy ending. Does this make sense? How the RQ value can change depending on the type of activity and type of fuel you're using to perform that physical activity? Yes? I promise you there'll be a question on this on the exam, all right? So let's talk about creatine and creatinine phosphate. So we see that creatine is going to be made from a couple of amino acids like glycine, arginine, these amino acids which help make creatine. And notice that this creatine phosphate, it's going to give up its phosphate to ADP in order to make ATP. Okay, that's how you have immediate ATP being synthesized when there's an initial burst of activity. And where the synthesis occurs is going to be in the liver, but the storage of majority of the creatinine phosphate in the body is going to be in your muscles. All right, so around 94% of the creatine phosphate will be stored in the muscles. And we find that around 2% is going to be regularly excreted in the urine, and so by measuring the amount of creatine in the urine, you can actually determine what is the amount of muscle in the body, right? So if you have more muscles, then your body is going to store more amount of creatine phosphate. And I would just want to highlight the difference between the term creatine and creatinine. Both have different structures, and creatinine, as the number 9, has like this ring-shaped structure. Creatinine also has the ring-shaped structure, and that's how it is going to be excreted in the urine, right? So How many of you have heard about creatine supplements? Okay, excellent. Do you think it will work if you are a long distance runner? Yes? Okay, no, it will not work, right? Because it's only going to be beneficial when you're engaging in a short burst of activity. Maybe you're trying to do pull-ups. No one is going to do pull-ups for 3 minutes, right? So for those initial burst of activities or your weightlifting, high intensity activities, creatine phosphate is going to be beneficial. But if you're engaging in an endurance activity, please don't waste your money on that. So again, just to repeat how the RQ value changes with the type of fuel being used. Notice that when you have maximum fats being used and low amount of carbohydrate, the RQ value is around 0.7. But then as you start using more and more carbohydrates and less fat, the RQ value gets to close to 1. And if you are using both carbs and fats as when you're at rest, then we see that the RQ value will be around 0.85, somewhere in the middle. So just to see if you understand what I've said until now, let's do a quick poll review question. All right. A person with an RQ value of 0.8 is most likely doing what? Resting, using glucose as a substrate to make ATP, exercising vigorously, using fats as a substrate to make ATP. Talk to your TAs, you can talk to each other, and we can answer this question. Okay. Most of you said resting, right? And I think exercising vigorously can also be a potential option if I'd given you a time stamp. If I said exercising vigorously for like 5 seconds, then you would have made that's a possible option, right? But we see that because there was no time mentioned, resting would be the best option, because intense vigorous exercise could happen with a initial burst of activity for up to 10 to 15 seconds, but that also would not change the RQ value. So now let's talk about muscle performance and how it can depend on the various types of fiber. Right? So we see that long distance runners, if you were to examine their muscles, they would have these slow fibers, whereas middle distance runners would have more of the intermediate fibers, and those who are sprinting, if you examine their muscles, they will have these fast fibers. So let's see what are the various difference between slow fibers, intermediate, and the fast fibers. And whatever I tell you in terms of slow and fast fibers, intermediate will be somewhere in between. So the first thing we notice is that the diameter of the slow fibers is going to be much smaller than the fast fibers. Right? They're going to be much greater in diameter, and also the amount of blood supply is going to be greater in the slow fibers compared to the fast fibers. And we see that the reason why you need more vasculature in these slow fibers is because the types of substrates used by the slow fibers would be mainly fats, and that's why you need a lot of oxygen being delivered to those muscles so that they can use aerobic metabolism for making ATP. Whereas these fast fibers, they mainly contain glycogen, and storage of glycogen requires more space, and we can see why these have a larger diameter as well. And we also find that the contraction speed, as the name indicates, in fast fibers will be a lot faster compared to the slow fibers. And the reason for this is because of the type of proteins which are found in the fast versus slow fibers. So let me give you an example of one protein, right? There are over 1,000 proteins which make up muscle tissue, right? But let me give you one example which you're all familiar with, myosin. So the myosin heads in a fast fiber, it's going to hydrolyze ATP a lot quicker compared to a myosin in a slow fiber. Secondly, the time for which the myosin head is bound strongly to actin will be shorter in the fast fiber. So the dwell time of myosin on actin is going to be shorter in the slow fiber compared to the fast fiber. Right, so those are just a couple of examples to explain why you have the contraction speed being faster in the fast fibers. And last point is that in terms of fatigue resistance, the slow fibers will have greater fatigue resistance because it is generating ATP through the aerobic metabolism. So it is going to take a longer time for this muscle to get fatigued compared to the fast fibers. So here's a quick polar vortex question. Glycogen would be used as a fuel by blank fibers, whereas fats would be used by blank fibers. So a simple question, yes? Easy? Cam? Okay, most of you picked option B, that is correct. Fast fibers would use glycogen and slow fibers would mainly use fat. Okay, so the question is, how can we get more fast fibers or more slow fibers, right? And simple but very difficult answer is through physical conditioning, right? So if you are a long distance runner, you can develop more and more of these slow fibers through conditioning. But it's not only conditioning, but also genetics plays a role as well. For example, if you take a look at the muscles in your eyes, they move around very quickly, and so they'll have fast fibers, and it's not because of conditioning but because of genetics. Maybe if you're a pianist who plays classical music and not just chords like me, you'll probably have fast fibers in your hands as well. And these are just pictures showing you how that in the fast fiber the diameter is much greater than in these slow fibers, which are found in a muscle known as the soleus muscle. This is a muscle which is helping you to stand for long periods of time. So you have mainly the slow twitch fibers here. We also find that these slow twitch fibers, they are darker in appearance because they have oxygen being stored in proteins known as myoglobin. Right, and we will look at the difference between myoglobin and hemoglobin when we talk about how oxygen is transported in the blood. But let me give you one last point before we end, right? How do you impress your family at Thanksgiving if you guys are not vegan, right? So we talk about red meat versus white meat. So we see that in the breast muscle, it's going to be mainly white meat because you have the fast twitch fibers which use the glycolytic pathway, because if the bird has to escape from a predator, it can fly away quickly using the fast twitch fibers in the breast muscle. Whereas since the bird is standing around all day and eating, it's going to have these slow twitch fibers in the legs, which is why the legs and the thighs, they would have the darker meat, which is going to use the aerobic metabolism. Let's end with one last question. Muscles with predominantly blank fibers are most resistant to lactic acid buildup. Is it fast, slow, intermediate, none of the above? Okay, most of you said slow, and that is correct. And we'll talk about fatigue when you come back tomorrow. Thank you all for your time.